video lecture for Chapter R, Session 3. This is for MAC 1105, College Algebra. My name is Jorge Gavillan. So these are the three objectives that we're going to be doing for this section. So we're going to go ahead and use the Pythagorean theorem and its converse to solve problems. So here we have a right triangle. We have leg A, leg B, and the hypotenuse side C. And we have a 90-degree right triangle. So in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the length of the legs. That is, in a right triangle as shown in figure 16. So C squared is equal to A squared plus B squared. Now, to find the hypotenuse of a right triangle. In a right triangle, one leg has length 4, the other has length 3. What is the length of the hypotenuse? So we can go ahead and use the theorem with A is equal to 4 and B is equal to 3. So we know that C squared is equal to A squared plus B squared. We input the values that we have, and we get that C squared is equal to 25, and C is equal to the square root of 25, which is 5. Now, the converse of the Pythagorean theorem is in a triangle, if the square of the length of one side equals the sum of the squares of the length of the other two sides, then the triangle is a right triangle. The 90-degree angle is opposite the longest side. So here we have a leg of 12, leg of 5, and a leg of 13 with a right triangle. So we're going to go ahead and apply this theorem. So the Willis Tower in Chicago, Illinois is 1,729 feet tall and has 108 floors. Observation deck is about 1,354 feet above ground. How far can a person standing on the observation deck see with the aid of a telescope? So we're going to go ahead and use 3,960 miles for the radius of the Earth. So here we have this information. So from the center of the Earth, we're going to draw two radii, one through the Willis Tower and the other through the farthest point a person can see from the observation deck. We're going to go ahead and apply the theorem. So since 1 mile is equal to 5,280 feet, 1,354 feet is equal to 1,354 divided by 5,280. So here we have the formula. So d squared plus 3,960 squared is equal to 3,960 plus 1354 divided by 5280 squared. And you can see that the distance when we solve it is approximately 45.08. So a person can see a little more than 45 miles from the observation deck. So here's some geometry formulas that we're going to use. Area of a rectangle is length times width. The perimeter is 2 times the length plus 2 times the width. Triangle, the area is 1/2 the base times the height. Circumference of a circle, the area is pi r squared. Circumference is 2 pi r, which is equal to pi times d, which is diameter. Closed rectangular box, the volume is length times width times height. Surface area is 2LH plus 2WH plus 2LW. A sphere, the volume is 4/3 pi r cubed, and the surface area is 4 pi r squared. So here we have a closed right circular cylinder. The volume is pi r squared h. Surface area is 2 pi r squared plus 2 pi r h. So using geometry formulas, a Christmas tree ornament is in the shape of a semicircle on the top of a triangle. How many square centimeters of copper is required to make the ornament if the height of the triangle is 6 centimeters and the base is 4 centimeters? So here we have the diagram. So the amount of copper required equals the shaded area. So this area is the sum of the areas of the triangle and the semicircle. So the triangle has a height of 6 and the base of 4. The semicircle has a diameter of 4 and its radius is r is equal to 2. So the total area is equal to the area of the triangle plus the area of the semicircle. And here we have the formulas. Input the values that we were given. So we're going to need about 18.28 centimeters squared of copper to complete this ornament. Next thing is we're going to understand congruent triangles and similar triangles. So two triangles are congruent if each pair of corresponding angles have the same measure and each pair of corresponding sides have the same length. So here we have two triangles. So here we have that A is equal to D, B is equal to E, and C is equal to F. You can see that the angles are also equal. So here, determining congruent angles, we can use angle side angle, we can use side side side, and we can use side angle side. So here's another definition. Two triangles are similar if the corresponding angles are equal and the length of the corresponding sides are proportional. So here we have a figure with similar triangles. A, B, and C for one triangle, and then D is equal to 2 times A, E is equal to 2 times B, and F is equal to 2 times C. Again, the angles are all the same or equal. So determining similar triangles, we can use angle, angle, or side, 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 or side, angle, side. So here's an example. Given that the triangles in figure 24 are similar, find the missing side length x and the angles A, B, and C. So because the triangle is similar, corresponding angles are equal. So A is equal to 90 degrees, B is 60 degrees, and C is 30 degrees. Also, the corresponding sides are proportional. That is, that 3 over 5 is equal to 6 over x. So we solve this equation for x. We get that x is equal to 10. So the missing length is 10 units. Here, again, we have the proof of the theorem that we talked about earlier. I'm not going to spend too much time on this. And then again, we've got the proof of the converse. Again, not too much time to spend on this. And this is the end of section R.3. Thank you.